So welcome everyone. My name is Anna May. I'm the Communication and Outreach Officer at ICMAB, the Institute of Material Science of Barcelona. And as you know, since April 2020, we have been organizing these seminars online, so we can also be in touch and learn new things every week or every 2 weeks. As you know, the seminar will last like 45-50 minutes, and you will be able then to ask some questions to the speaker by using the questions and answer button that you have at the bottom of your screen, or also using the chat. If you wish to talk, you can also ask, and we can give you allowance to talk. So today we have with us Begoña Abad, and she is hosted by Ricardo Rurali, who is a researcher at the ICMAB, and will now introduce her to all of you. So thank you for being here, all of you, and see you later. Ricardo?
Yeah, thanks, Anna. Welcome, everybody, to my living room. As Anna said, today we invited Begoña Abad. She's now a postdoc. She's doing her second postdoc. She's working in Switzerland, the University of Basel. And she started a research career doing a PhD in Madrid, in the Microelectronic Institute. That I guess in the meanwhile changed name or something. Now it's something related, but you know, perhaps you know the place I refer to. Between these two jobs, she spent I guess a couple of years in the United States, in University of Boulder, University of Colorado Boulder. So I kind of know what she did in her PhD thesis and what she's doing now. I'm not so familiar about her work in the US, and so I thought that rather than asking her about it, it was easier for me to invite her to give a talk in the Institute seminar cycle. And so here she is. I will leave the floor or whatever, I mean the screen, to her for the next maybe 45 minutes. Okay, thanks everybody, and Begoña, the floor is yours now.
Okay, good morning, everyone. First of all, I would like to thank you for the invitation. I wish I could be there in person, but at least we can stay connected thanks to these platforms. So as Ricardo mentioned, I did my PhD in Madrid, then I moved to the University of Colorado Boulder, and then now I'm doing my second postdoc at the University of Basel. So today I wanted to talk about my work at the University of Colorado Boulder. It was carried out at JILA, which is an institute joined between CU Boulder and NIST. And I'm going to be talking about thermal transport and mechanical properties characterization using a particular type of light, which is extreme ultraviolet coherent light. So I have divided the presentation in several parts. First, I will give a motivation about what is useful, this light, and what type of things we can characterize with it. And then I will focus on two main blocks. First of all, I will talk about the observation of non-diffusive thermal transport in two systems, both silicon and also silicon metalattices. And then I will start talking about the mechanical properties also on these silicon metalattices and another type of materials, which are ultrathin films systems. Then I will briefly mention my work on developing a fully non-destructive technique, which is called EUV transit breaking technique. And I will summarize my work at CU Boulder. And I will finally give a very brief introduction on my recent work at the University of Basel, which is focused on advanced Raman spectroscopy. Okay, so the motivation of my work at CU Boulder relies on the nanoscale revolution. Of course, nanofabrication techniques now allow us to fabricate feature sizes that are really, really small. So from those size scales, there are physical properties that dramatically change, and we really want to understand why and how. So to do this, we need new metrology techniques, because conventional techniques really struggle to probe these very small systems with dimensions below 100 nanometers. And we really want to understand these fundamental physics at the nanometer length and also femtosecond and nanosecond time scales. So we want to develop in situ non-destructive, non-contact metrology to understand these material properties and also energy transport on different kinds of systems. So in my case, I was focusing mainly on nanoscale heat transfer. And this is a field that is really important to characterize features on the very small sizes, because macroscopic models really break down. And they break down especially when the carrier mean-free path is on the order of the feature size. So for dielectrics and semiconductors, the main carrier is a phonon, and the phonon mean-free path is it can range from 1 nanometer to even 10 microns. So it's really easy to achieve these features on the order on the phonon mean-free path. And this is also not only important from a fundamental point of view, but it also has very technological applications like heat management, thermoelectricity, or photothermal therapies. On the other hand, my work was also focused on the study of elastic properties. And here we want to characterize dimensions below 10 nanometers because the elastic constants sometimes differ from the bulk counterparts. In this case, for example, a thin film below 10 nanometers is extremely difficult to characterize because it's really difficult to decouple the properties of a thin film from those of the substrate. So, okay, when we want to characterize features in the nanoscale, we really need to go also to the ultra-fast times. So features in the nanoscale sizes, we can find phonons, spin dynamics, molecular vibrations. So we need to go from nanoseconds to femtoseconds. And we happen to have this very useful tool based on extreme ultraviolet light, which is created by high harmonic generation, and it has nanometer wavelengths. It's a tabletop source, so it's available 24/7, and you don't need to go to a big facility to do experiments. It's also coherent and laser-like, and the pulse duration of these beams is as short as 10 femtoseconds, so you can really do a very well-resolved in-time experiments. So with this light, in my previous group, we were able to do many different works, from studying the elastic properties of very thin films to do imaging of buried layers. Also, we did dynamic imaging. This is recording movies of the surface of a nanostructure moving in real time. Some spin dynamics, and of course, we were able to probe thermal transport, which I will be focusing on in this talk. Okay, so let me introduce the main technique that I was using during my postdoc, where I was using this extreme ultraviolet light in a pan probe configuration. So we typically say it's a pan probe spectroscopy because we have our sample, which is, it can be either a bulk material or a thin film or a metalattices that I will talk about later. And we put some metallic lines on top of it. Okay, so then we use a pan beam. It's an infrared beam, ultra fast, 25 femtoseconds. And we use it to heat up this metallic grating. So the light is preferentially absorbed by these lines. And there is a rapid heating, which is followed by the impulsive thermal expansion. So when these lines expand, they also launch acoustic waves into the nanograting and the sample. And finally, the nanostructures transfer the heat to the sample and relaxes to the original profile. So we use different sizes for these nanolines, different geometries, line widths ranging from 30 nanometers to 1 micron. And also we control the period between these nanolines, which is very important, as I will explain later. Okay, so we launch our dynamics, but we need to probe them. And here's where we use the extreme ultraviolet light. We use this light generated by high harmonic generation. And in our case, we use a 30 nanometer wavelength. This allows us to probe structures down to 15 nanometers, which is well below the diffraction limit of the visible light, and we can probe picometer scale displacement of our nanolines. Moreover, this is sensitive mainly to the surface profile. And as I said before, due to the short duration of the pulse, we can do ultrashort time resolved measurements. So here I wanted to show how our experimental setup looks like. We have a titanium sapphire oscillator and then an amplifier. So that from the amplifier, we get laser beam, which is really intense, is millijoules and really short, around 25 femtoseconds. And then we split this beam in two different arms. One of the arms is the pump that will be pumping our nanograting, and is passed through a delay line, which allows to control the time between the pump and the probe. So then this arm pumps the sample, and then we have the other arm, which is the probe, and this infrared laser beam is focused on an argon filled hollow fiber where the high harmonic generation takes place and upconverts the light from 800 nanometers to 30 nanometers. So this light is focused on the sample, on the grating, and is able to track the diffraction of the nanograting as a function of the delay between the pump and the probe. There is a slightly modified version of this setup where instead of using the nanograting on top of the sample, we just create an interference pattern with two beams on our sample. So that interference pattern gives rise to a sinusoidal temperature profile, and we just probe also the diffraction of that interference. Okay, this is a simulation of the signal that we measured. This is a nano line. This is the surface displacement after pumping it. And this is the diffraction that we record in our camera. So we see how there is a change in diffraction. So we sum up these pixels in a specific way and we get the change in diffraction. As you can see, there are different features that are related with either acoustic dynamics and also with decay, which is the thermal transport given by the substrate. So here we can say that we are able to do acoustic, we are able to probe acoustic dynamics and thermal transport in a single measurement. So a little bit more detail. Here is the typical trace or raw data that we get. This is the system. We pump with our infrared pan and we probe with the EUV probe and record the diffraction pattern. This is the typical signal that we see. And as I was saying, first we see the thermal decay, but there are some acoustic waves here superimposed that are given by the nanolines acting like hammers and creating these surface acoustic waves whose frequency we can extract from the Fourier transform of this signal. Finally, if we go to very short time scales, we can see here these oscillations that are given by the nanostructure itself resonant mode. And finally, there are other features here that happen when we have a thin film on top of a substrate, and those are just echoes. Is a reflected longitudinal acoustic wave reflected off the interface. Okay, so with this technique, we were able to study thermal transport and also mechanical properties. So I will start talking about this non-diffusive thermal transport that we were able to see in both bulk silicon and silicon metalattices. So this non-diffusive thermal transport is very important because it happens when the characteristic dimensions of the systems happen to be on the same order as the phonon mean free paths. So phonons are the main heat carriers in semiconductor and dielectric materials, and the wavelengths are below 5 nanometers, and the mean free paths, as I said before, range from 1 nanometers to 10 microns. So when the length scales become comparable to mean free paths, bulk models break down, and it was already proved for many systems with different geometries and different materials. So in our case, we focused on nanoscale heat sources. And we want to understand how this diffusive, non-diffusive thermal transport works, because understanding heat transport is critical for technologies and also from a fundamental physics point of view. So now I'm going to explain how we quantify this non-diffusive thermal transport, which is not trivial. So we relied on diffusive thermal transport. We use the Fourier's law, which describes the thermal transport in materials. And what we have here is our nanoline on top of a substrate. And we do a finite element simulations with our nanoline, and we create a temperature profile in order to fit of our experimental results. So we know that between the nanoline and the substrate, there is a thermal boundary resistivity, which is intrinsic to every two materials that are put in contact. In this case, the nickel and the silicon. So if we use the thermal boundary resistivity intrinsic to these two materials and fit our results for an nanoline that is very small, 60 nanometers, we see that the fitting is not really good. So if we let this thermal boundary resistivity vary, we see that there is actually a change on this parameter, and we need larger value of this parameter to be able to fit our results. And this correction is what we use to quantify the non-diffusive thermal transport. We did that with this analysis for different nanogratings with different line widths. And we could see that as we were reducing the line width more and more, this parameter that I was talking about, the effective thermal boundary resistivity, increases and increases. And this is a sign of quasi-ballistic transport that predicts that this thermal boundary resistivity goes up. Not only that, but if we study also as a function of period, we see that there is a turnaround in the behavior towards diffusive predictions when the period starts to be also comparable with the phonon mean-free path. We did that for two different substrates, sapphire and silicon, and we saw the turnaround happening at the lengths that happens to match the phonon mean-free path of these two systems. So from these studies, we could see that the nanoscale heat sources cool more quickly when placed together than when they are widely separated. And this was called collectively diffusive regime. In order to corroborate this, we did another experiment, which was based to not only keeping the a constant duty cycle. This is the blue line, where you keep the same proportion of nickel in your nanograting, so that as you reduce the nickel line width, the period is also reduced. And this is when we see the turnaround. But we kept the period constant. That is, when you reduce the line width, the lines are more and more isolated. And here we could see that doing that, keeping the period constant, recovers the monotonic quasi-ballistic behavior. Moreover, we did that also with fused silica, whose phonon mean-free path is 2 nanometers, and we saw no deviations. Of course, because the phonon mean-free path is so small that the nanolines and the periods are always larger than this phonon mean-free path, so a diffusive transport is expected. So once we characterized these bulk materials, we went beyond these simple materials and started studying more advanced ones. In particular, the silicon metalattices. The silicon metalattices are artificial 3D solids, periodic on a scale of 1 nanometer to 100 nanometers. And they are made from a 3D periodic template of silicon nanospheres, where our collaborators infiltrate silicon between the spheres, and sometimes they were able to etch out the silica spheres. So at the end, we have this kind of structures where we have more capacious regions called meta-atoms, and that are joined by meta-bonds. These scales are on the order of few nanometers. So here you can see how this structure looks like, where you can see the meta-atoms and meta-bonds, and are really in the deep nanoscale. Okay, the main interest of these materials was studying heat transport on these metalattices because these are phononic crystals, and this allows us to manipulate heat. So when you arrange two materials in a periodic manner, depending on the size of the period, you are able to manipulate sound or hypersound, or even if you go to sufficiently small periods, you're able to manipulate heat. And this is the case for these nanostructured materials. So the main motivation here would be thermoelectrics, because the phonon transport would be impeded, but the electrical conduction remain constant. So there are a few works on those types of structures from a theoretical point of view. There are molecular dynamic simulations, and they show a really dramatic reduction on thermal conductivity. But of course, this is for a few nanometers sphere size. On the other hand, there are also some experimental works on metallic metalattices on the order of 100 nanometer sphere size, and semiconductor ones of the order of 300 nanometers. So in this work, we are somewhere in between, because we have metalattices with a sphere size on the order of 14 and 13 nanometers diameter. So this is 10 times smaller size than the experimental state of the art. In this case, we measure the metalattices with the spheres still inside the metalattice. Okay, so now I'm going to show some of the results that we got. As I said, we measured two samples. One is made of 30 nanometers diameter spheres, and the other one is 14 nanometers in diameter. So we have different gratings with different periods and line widths, and we do our pan-probe spectroscopy. So when we do that, we get this type of signal, which is really good in terms of signal-to-noise ratio. We can clearly see the acoustic waves and the thermal transport. And when we analyze the thermal decays, we want to compare with macroscopic predictions. And from macroscopic predictions, we know that the effective thermal conductivity of these metalattices should be something around 3 to 8, and they should be independent of the grating geometry. However, when we analyze it as a function of the line width, we see that there is a trend. So there is a dependence of the line width on this material again. And if we compare with the plot that I showed later, we found a really similarity between the two, because in this case, this was effective resistivity, and this is effective thermal conductivity. So one is the inverse of the other. So at the end, they are very similar. So something similar to what was happening on the silicon is also happening on this type of metalattice. Also, if we look at the 14 nanometers diameter metalattice, we see also the same kind of behavior. So to try to understand this behavior, we are wondering about different phenomena that could be explaining this, and we are wondering if this is coming from ballistic phonon transport, from phonon localization, or even from interface phonon scattering. So in order to understand this a bit better, our collaborators in Penn State University are performing molecular dynamics on this type of systems to understand the heat exercise effects on these silicon metalattices. Okay, so now I move to the mechanical properties on these silicon metalattices and also in ultrathin films. Okay, so before I explain this technique, but now I want to focus more on the acoustic waves part. And one of the very important things of this technique is that we are able to tune the penetration depth of our waves just by tuning the period of these gratings. That is, the acoustic waves has a wavelength that is given by the period. And the penetration depth is just the period over pi. So if we are able to tune the period between these lines, we are able to tweak this penetration. That means that for large periods, the acoustic waves reach the substrate. But if we go to sufficiently small periods, we are able to confine the wave within the film. And this allows us to decouple the properties of the thin film from those of the substrate. Okay, so in the same measurement as I saw before, we could analyze thermal transport, and of course we can analyze also the acoustic part, the mechanical properties. Again, we study the 30 nanometer silica sphere and also the 14 nanometers one. We do our pampa spectroscopy. This is an image, an AFM image of our nanolines on top, and we see how they conform the surface of our metalattice. And then we study the frequency of these acoustic waves. So if we extract from Fourier transform the frequency of these waves, we are able to calculate the velocity of these acoustic waves inside the metalattice. And here it is plotted. This is the measured surface acoustic wave velocity as a function of the soil penetration depth normalized by the thickness. And we have this trend that can be explained as a function of the penetration depth, as is here, because for sufficiently large penetration depths, we recover the speed of sound of the silicon, which is around 5,000. But if we are able to confine the wave sufficiently, we are able to recover the velocity of the metalattice. This is calculated from finite element analysis, and we see how when we have the waves totally confined, we recover this value. This tunable of the tunable penetration depth allows us to access different information. So from the very confined acoustic waves, we have access to the properties of the metalattices. So from there, we can extract the Young's modulus and also the filling fraction. This is the percentage of silica that we have really in our metalattices. And we did that, and we extract different values of Young's modulus for these three different ratings. And we saw that they are in very good agreement with theory, which is based on continuum mechanics, and also with another independent technique. In this case, we did nano-indentation. So that's from the fully confined waves. But we can also use, once we know the mechanical properties of our metalattice, we can use the big ratings to access also other type of information. In this case, as the wave are reaching the substrate, we can extract the thicknesses. And we compare also with SEM, and we found that we could get this information in a good agreement. So from this spectroscopy on this type of complex materials, we can say that we were able to non-destructively measure the Young's modulus, the filling fraction, and the thickness of these 3D nanostructures, which has sub 100 nanometers periodicity. And we saw that the mechanical properties follow the macroscopic predictions. So we can design these metalattices with predictable mechanical properties, but they still have an exotic thermal behavior that we need to understand better. Okay, so now I change a little bit to the ultra-thin films. So in this case, the motivation to study these low dielectric constant films is that these low dielectric constant dielectrics are critical for nanoelectronics. So we really want to have a very low dielectric constant to increase the transistor switching speed, and also to decrease the parasitic capacitance that happens between the metallic connections. However, when we reduce this dielectric constant, what happens is that mechanical properties get degraded. So for example, we can get some delamination or creep. So this is really challenging because we need to find a compromise between good mechanical properties and still good dielectric constant. So this is the motivation for us to measure a really extremely thin film dielectric constant, low dielectric constant films. And how do we do that? As I said before, it's really challenging to extract the mechanical properties of films well below 100 nanometers using current techniques, because the properties are typically coupled with those of the substrate. So in our technique, we are able to decouple them by confining the waves within the film. And we are able to extract both Young's modulus and Poisson's radio. And the way to do this is from the echoes that I was explaining before, the reflections from the interface, we are able to extract the C11 component of the elastic tensor. And from the surface acoustic waves, we are able to extract the C44 component of the elastic tensors. So from these components, we can finally extract the Young's modulus and Poisson's ratio with that tells us about the stiffness and compressibility of our materials. So these are the main results that we got. First, we studied a thin film, which is made of a bilayer. This is 46 nanometers film, and we extract the Poisson's ratio and Young's modulus, and then we measure the same material with a lot of reduced thickness, and we saw that there's a substantial softening in this thin film. This happens because this is a lowly doped sample, but if we do the same study on samples with different thicknesses, but that are highly doped, this highly doping is used to reduce also the dielectric constants. We see no difference between the mechanical properties of the three films. So we see that for lowly doping, there is a dramatic softening of the properties, but if the film is already highly doped, there is no difference. And here you can see how the highly doped is on the order for the Young's modulus of the very thin layer. And how can we explain this? So we explain this from a rigid bond network point of view. If we look at the bilayer, at the thick, it is 46 nanometers, but it is still thick compared to the 5. So if we look at the rigid bond network, we see that the bond terminations from the surface are not enough to affect the mechanical properties. But when we are in a very thin layer, these bond terminations given by the surface really affect our mechanical properties, creating this softening of the mechanical properties. And on the other hand, for the hydrogen, this highly doped is actually hydrogen doping. When it dominates, it creates within the network, it disrupts the bonds and is able to create also this softening of the mechanical properties. So both surfaces and doping can induce an order of magnitude softening. Okay, and then I will briefly talk about some work I did on developing a system called EUV transient grating technique, which is completely fully non-destructive. So I mentioned before that we were using also a technique called visible transient grating, which is based on two beams crossing at the sample, creating an interference pattern, which creates a sinusoidal temperature pattern. And from that, we can probe the dynamics with our EUV beam. But of course, this is diffraction limited excitation, and we cannot get periods down to lower than 1 micron. So in order to fully explore nanoscale effects, we really need to make this period smaller. And this period depends on both the angle and the wavelength. So if we are able to cross two beams with dramatically reduced wavelengths, we will be able to explore periods really, really small. And this is what we wanted to do in this experiment, to have a truly non-destructive and in situ measurements, because in this case, we wouldn't need the fabrication of the metal nanolines, and we could reach periods down to 15 nanometers. However, this is extremely challenging because working with this type of light requires using vacuum because this light gets absorbed within a micron since it's created, and also refractive optics don't work for this type of light, so we need to use special optics, and the flux is also an issue where you lose a lot of flux when using this reflective optics, and it's engineerily really challenging. So we started from doing UV pump and visible probe, and as you can see here how the system looks. This is the vacuum chamber, and we have this is a toroidal mirror that is able to focus our UV light onto a mirror that splits the beam on 2 mirrors, and then these 2 mirrors recombine the beam on the sample. So these 2 beams are able to excite and create this sinusoidal pattern, and then with another beam, we were able to probe the dynamics with a visible probe. So next step is moving from this visible probe to fully EUV to be able to access these really small periods. Okay, now the summary of the work at CU Boulder. From the non-diffusion thermal transport point of view, we were able to validate the collectively diffusive in silicon, and also in the metalattices, we saw how the heater size affects the thermal transport, that there is a dependency, even is not predicted from the macroscopic point of view. So this also proves that there is non-diffusive thermal transport. From the mechanical properties point of view, we studied the silicon metalattices, and we saw how we could design from continuum mechanics point of view. We can create these predictable mechanical properties, but still have exotic thermal transport. And the ultrathin films study told us about how there was a substantial softening due to doping and surfaces. Moreover, we were developing this other fully non-destructive setup, which is the UV transient grating, and it would be the first tabletop implementation of UV pump and visible probe experiment. So now let me talk just very briefly about the work that I'm doing at University of Basel. So my work is focused mostly on Raman spectroscopy. Just very briefly, this is a 2-photon scattering process where there is a photon interacts with the material and it gains or loses energy, giving you the anti-Stokes scattering or Stokes scattering. And you can probe this and get it together with the Rayleigh scattering. And from these features, you can learn a lot of things from chemical composition to strain and more information. So in the group, we are doing a lot of Raman spectroscopy, but in my case, I'm focusing on advanced Raman spectroscopy. And when I say that advanced, I mostly want to say pan-probe Raman spectroscopy, where we are going to do time resolve spontaneous Raman spectroscopy, where we will looking at phonon lifetimes. In this case, we will use a pump in the femtoseconds time pulse duration, and we will use a probe in the picosecond pulse duration to be able to extract the phonon lifetimes. However, that is sometimes complicated and it requires a lot of time and the signal is weak. So we will use stimulated Raman spectroscopy or coherent anti-Stokes Raman spectroscopy, in which we use 2 different lasers, which are whose frequencies actually matches the frequency of the phonon that we want to study. And this process increases the efficiency of the process by 10 to the 6. So this will allow us to see features that are not possible to see with conventional Raman. Finally, we will extend this technique to time resolve stimulated Raman spectroscopy and also time resolve coherent anti-Stokes Raman spectroscopy, where we will not only have these 2 beams whose frequencies difference matches the phonon frequency, but we'll have a pump before so that we will put our system in an excited state and we will probe the dynamics of that state. With that, we will be able to probe coherent effects on different systems, and we will also do especially resolve Raman spectroscopy and also time resolve. And this is a view of the current setup that we are developing. I'm happy to discuss it later, but it's basically a pump which is split in 4 different beams to be able to have all the options that we want to use to excite our system. We have here something called pulse shaper, which is able to tune the pulse duration from femtoseconds to picoseconds. So we are able to tune the resolution of our setup, in the spectral resolution. And finally, we have a triple spectrometer and a CCD camera. So with this setup, we will be looking at superlattices nanowires, which are new materials with new properties arising from interference effects at the superlattices. We will also probe hydrodynamic thermal transport into the materials. And not only with this setup, but just with conventional Raman, we are doing thermal conductivity measurements by Raman thermography, where we are able to probe the temperature profile of a suspended nanowire, and applying a thermal model, we are able to extract the thermal conductivity of different nanowires. And with this, I would like to thank my previous group, Kapteyn-Murnane group, and all the colleagues that I work with, and also the metalattice fabrication and molecular dynamic simulation collaborators from Penn State, also the nanolines for fabricated Berkeley lab. And I would like to thank to all my colleagues at Sardo group in the Nanophononics lab. And with that, I thank you for your attention.
Okay, thanks, Begoña, for the presentation. I'm new to this, but I think I was able already to get a couple of questions in the question and answer. Maybe you can also read them you as well, but I will do this for you, so I give some sense to my being on the screen right now. So the first question is from Philippe Sandiumenge, who is a researcher at our institute. I guess the question is about the part on the mechanical properties, and if not, Philippe will correct me. And he's asking, are these film epitaxial? If this is the case, what is the influence of the substrate? Can this method be extended to characterize the mechanical properties of freestanding films?
That's a very good question. And this is something that I've been wondering also about, because I'm pretty sure the properties would be different if you have them freestanding. However, we are still interested in having these films supported, because this is how they are. So this is a collaboration with Intel, and they provided us with a system that they are planning to integrate in their circuits, in their devices. So they are still interested to know if these systems work in the type of device that they would create. But I'm totally sure the substrate would have an influence in the sense that of the bonds between the film and the substrate. Because from the measurement point of view, we prove that we are able to isolate the properties of the film itself from the properties of the substrate. So I don't know if that's clear.
Okay, thanks. Then we have another question from Alexander Bloch. Yeah, Philippe saying yes, thank you. So he liked the answer. Is from Alexander Bloch. I believe he's connecting from our neighboring institute of the nanoscience and nanotechnology. He's thanking you for the very nice talk, and he asks you to comment on the validity and assumptions of the extraction of the RF, the effective resistance, I guess, from the finite element simulations.
Okay, so this extraction of the effective resistivity is just a way to quantify the non-diffusive thermal transport. So the assumptions that we make is we just model the nanolines on top of our substrate. We use the AFM sizes and everything, and we recreate the surface deformation of our nanolines. And with that, we have diffraction code, so that we are able to diffract off our surface simulated by console. And then we create, we actually create all the simulations for different values of the effective resistivity. And from all those values, we're able to fit our results to one single value of the effective resistivity. So I don't know what Please, Alexander. He refers to validity, but to us, this is valid because it's just an effective model to quantify the non-diffusive behavior. So it's to see how much it deviates. It's not a real value. It's not physical to some extent. It's just to quantify how different it is from Fourier predictions.
Yeah, this is actually something that I wanted to ask you. So thanks for the answer. Maybe just a follow-up question. What you look at is the deviation from the expected value. How do you know what is the expected value? Do you use some of this phenomenological model like the diffusive mismatch model or things like that? Or?
Yeah, that's a good question. We extract that value from a very long line.
Okay, almost so you measure it yourself.
Yeah, so okay. We measure it and we see how that, as you decrease the line, it starts increasing the resistivity.
Nice, thank you. Then we have, guys, a lot of questions. We have a question from Marina Campoy, who you might know. Nice talk, Begoña. For the porous silicon, is it crystalline silicon? Have you measured the macroscopic thermal conductivity and the electrical conductivity?
Okay, thank you, Mariana, for your question. We think it's polycrystalline because it's so small. The network created in these structures is so small that we think that it's created by really small crystals located in a way that made the system isotropic, but still polycrystalline. If we have measured the macroscopic thermal conductivity, we are unsure if the thermal conductivity extracted from the very big lines, if that can be the thermal, because typically when we use the big lines, we approach the diffusive thermal transport. So we could say that what we are measuring is following Fourier's law, and what we are extracting is really the thermal conductivity. At this point, we cannot claim that this is the thermal conductivity, but our collaborators in Penn State, they did TDTR and they extracted some values that are more or less in agreement, but we need to do more work. And regarding the electrical conductivity, we haven't measured it yet.
Okay, thank you. Maybe he can measure it. We'll ask him. We have another question from Hussein. He's asking if when you talk about non-diffusive and quasi-ballistic thermal transport, you're just using them in an exchangeable way, or you have in mind two different transport mechanisms?
Well, yeah, that's a very good question, because what we are trying now is to figure out what is the fundamental mechanism for these results. And we are doing two different approaches. One is following phonon hydrodynamics simulations, and also molecular dynamics. So when we say quasi-ballistic thermal transport, what we mean is that when we reduce the line with dimensions, the scattering events between phonons are reduced. And this is what happens this is by definition the quasi-ballistic thermal transport. You get less and less scattering events, and then your transport is less efficient. But it is true that at the same time, we are seeing from the phonon hydrodynamics point of view that this also plays a role, and there are some actually cold spots created next to the nanolines, and there is like kind of a vortex, thermal vortex next to the lines that could explain this phenomena. And from the molecular dynamic simulations, we are seeing how the lifetime of the phonons is changed as we reduce the line width. And this would be explained also in terms of reduction of scattering.
Okay, thanks. The same guy has also a short follow-up question, and he was wondering if we can refer to the non-local strain gradient to describe the thermal penetration and the deformation.
Can we refer to the non-local? I don't know if I understand the question. Okay. Can we refer to the non-local strain gradient?
Yeah, well, I guess by relation between the strain and the thermal penetration. But of course, this is what we miss in the real interactive seminar, that now the guys could stand up and clarify your question. But we have a further one, so I suggest we move on. We have a question from Xavier Rodriguez. Well, he's no longer a student because he got his PhD degree like last week in our institute. He works with organic films, so guess what? He's asking you if you have any experience in measuring organic films or any other species that might be sensitive to UV exposure. And also, how big is the EUV spot once focused on the sample? Andy, thank you for your presentation, but I skipped that part.
Yeah, this is also a very good question. I did measure some kind of organic. Well, it was actually all nanoparticles covered with ligands, and that was challenging because we needed to be really careful with the pump, not with the UV. Because it was easier to burn it, the sample. With the UV light, we didn't have that problem just because the flux of our beam is not really very intense. So this process, high harmonic generation, is still not super efficient. So we don't get a really powerful coherent beam. So from the UV point of view, the only problem that we have is that we create this carbon, the same as in the SEM, this carbon cracking phenomena where you cover your sample with a thin layer of carbon, but not we didn't alter the sample in any other sense. And how big is the UV spot is 100 microns diameter.
Okay, we have a final technical question by Darla Mar. Hi, nice presentation, and she or he is wondering if the talk is going to be online somewhere, and yes, it's going to be posted on the YouTube channel of the institute. So stay tuned, and you will find it soon. With that, in case there is no last-minute question, which seems to be the case, I would like to thank again Begoña for accepting our invitation and for making the effort to set up and join our presentation for us all. And also thanks to all the people that attended and for the interesting question asked. Okay, thanks, and see you around.
Thank you very much.